Hey everyone, welcome to the video on revisiting radicals. We're going to do a little bit of Pythagorean theorem, and then actually in the next classwork you're going to do segment review. So when we simplified radicals back in the algebra review part of this course, we did not do what's called rationalizing the denominator. And there were some examples, and I know I told my students, oh, when we get to that section you'll see that you cannot have a radical in the denominator. If you do start off with a fraction where you have a radical in the denominator, you have to do what's called rationalizing the denominator. So in order to rationalize the denominator, we need to get rid of all radicals that are in the denominator. So what we're going to do is, in order to get rid of this square root of 3 in the denominator, first of all, we cannot simplify 12 divided by the square root of 3 because one has a radical and one does not. So we cannot do that. So instead, what we do is we multiply the numerator and denominator by whatever the radical in the denominator is. Because really, what this number equals is 1. So as long as I multiply anything by 1, I'm changing potentially how it looks, but by multiplying by 1, I'm not changing the value at all. So here, multiplying across, when I have radicals, or when I have fractions, I multiply across, so 12 times the square root of 3 is 12 root 3, over the square root of 3 times the square root of 3 is 9. So now, hopefully you notice, wait a second, that's a perfect square. Well, that's the point of this, because now that I've made the denominator a perfect square, notice the radical goes away. Because like I said, rationalizing the denominator means we are getting rid of radicals from the denominator. So now, the numerator and the denominator, we can simplify this 12 and this 3. Because 12 root 3, 12 is a factor, it's not a term. If this was equal to, let's say, 12 plus the square root of 3 over 3, I absolutely cannot simplify those two, because that plus sign means my numerator has two terms, but when they're being multiplied, they're factors, so I could simplify factors. So this would end up equaling 4 square roots of 3. So you may be wondering, well, how did I know I want to multiply by square root of 3 over square root of 3? Why didn't I multiply square root of 7 over square root of 7? The reason is, don't forget that a radical times itself. So if I take square root of 7 and I multiply it by square root of 7, it is going to equal the square root of 49, which equals 7. So by multiplying a square root with itself, you release it from the radical jail. Watch again, square root of 5 times square root of 5. Square root of 5 times square root of 5 would be square root of 25. The square root of 25 is 5. The square root of 2.1 times the square root of 2.1. Guess what that's going to equal? 2.1. So whatever the square root is in the bottom, whatever value that number has, that's what you want to multiply the equation top and bottom by that same number. Because by multiplying a radical with itself, you always make it a perfect square, and then it's always going to escape from the radical jail, if you will. Okay, so let's take a look at number 2. The first thing I notice, if I look at this, is now I have a radical over both the numerator and denominator. Because that's the case, I could simplify this. I could reduce by 2, top and bottom, giving me the square root of 24 over 5. So now, with the quotient rule that we learned, when I have a radical over top and bottom, I could separate this, the square root of 24 over the square root of 5. I have two options at this point. I could simplify square root of 24 because I know that a 4 goes in there. I could simplify that first, or I can multiply root 5 over root 5, so I could rationalize the denominator. Let's say I do rationalizing of the denominator first, so that means multiply by square root of 5 over square root of 5. This gives me the square root of 120 over the square root of 25. This is going to equal the square root of 120 over the square root of 25 is 5. Now the square root of 120 can be simplified. I have to simplify this radical. So how would I do that? What perfect square is inside of 120? I know for sure 4 times 30 over 5. So now I would get 2 square roots of 30 over 5, and that's my final answer. The second way I could have done this, I'll do this in a different color. is I could have taken the square root of 24 over the square root of 5. Square root of 24 is the square root of 4 times the square root of 6, all over the square root of 5. Square root of 4 is 2 root 6 over the square root of 5. I still have to multiply top and bottom by the square root of 5 because I still have to rationalize that denominator. So now I multiply numerator times numerator. 2 square roots of 6 times the square root of 5 is going to be 2 square roots of 30 over square root of 5 times square root of 5 is the square root of 25. This ends up equaling 2 root 30 over 5. So notice that I do get the same answer here and here, regardless of which way I do it. So you can multiply first or you could simplify first. Either way, your final answer should be the same. All right, looking at example C here. We have 3 root 5 times the quantity square root of 10 minus 2 square roots of 5. So what we're going to do is we're going to go ahead and distribute here. We're going to do 3 square roots of 5 times the square root of 10. You don't have to show this step. I'm just showing you so you have it in your notes and you can refer to it. And then minus 3 square roots of 5 times 2 square roots of 5. Okay, so now I do 3 square roots of 5 times the square root of 10. The 3 has no one to be multiplied with because there's just that invisible 1 there, and I have square root of 50. Minus, here I can simplify, or I can multiply the 2 numbers on the outside. That's going to give me 6. And then the 2 numbers underneath the radical sign is going to be square root of 25. As always, I don't want to leave this as my final answer. I want to simplify. So square root of 50. What perfect square is inside of 50? 25 and 2 minus 6 times, well, the square root of 25 is 5. Let's keep cleaning this up. Square root of 25, that's 3 times 5 times the square root of 2 minus 6 times 5 is 30. Finally, we get 15 root 2 minus 30. There's nothing I could do to simplify those any further because one has a radical and one does not, so that is my final answer. All right, so looking at example D. I have a binomial times a binomial, so that is good old FOIL. So 6 times 6, my first, is 36. Outside, 6 times 3 root 10 is going to be minus 18 root 10, and minus because I didn't say that minus in front of there. Inside is going to be plus 18 square roots of 10, and then last times last is going to be minus 9 square roots of 100. Clearly, this is not my final answer. I want to clean this up and make sure that I have a final answer that's completely simplified. Pause the video, please, and simplify this on your own and check against my answer that I will show you in a moment. All right, your final answer, once you simplify everything, should be negative 54. If you did not get that, make sure you ask in class tomorrow, but I'm sure your teacher will go over it with you anyways. Okay, let's look at our last example here. We're going to solve for the missing side of the triangle. First thing I notice is this is a right triangle, so I know this is going to be a Pythagorean theorem problem. Pythagorean theorem we mentioned last chapter, or earlier in this chapter. You take the leg squared plus the leg squared, and it's going to equal the hypotenuse squared. All right, so it doesn't matter which leg you take first. If you take the bottom leg, x squared, plus the other leg, 7 squared, keeping in mind that the legs are the 2 sides that form the right angle. The side across from the right angle is the hypotenuse. So this is going to equal 5 square roots of 3 squared. Let's clean up the left, let's clean up the right. I get x squared plus 7 squared, which is 49, equals. Now, when you have a value like this, I like to show kids that you multiply 5 root 3 by itself, so times another 5 root 3. This side, I can't do anything with it. This is going to equal, I can multiply 5 times 5, I get 25, square root of, and then I multiply 3 times 3, and I get 9. Well, looking at the right side, I have 25 times a perfect square. So when I simplify that, I am going to get 25 times the square root of 9 is another way to write the number 3. So x squared plus 49 is going to equal 75. Remember that entire few days that we spent solving quadratics, I see that this is a square rooting problem because I only have an x squared, so I'm going to subtract 49 from both sides. I get x squared equals 26. Are there any perfect squares inside of 26? Well, 25? No. 16? No. Does 9 go into 26? No. Does 4 go into 26? No. So I square root both sides. Typically, you get x equals, and you always get plus or minus the square root of 26. However, x now is not just some arbitrary number. X represents the leg of a triangle. So a triangle has to have sides that are positive numbers. So we actually don't include the negative square root of 26. It's just going to be the positive 26. Algebraically, yes, you get two answers, plus or minus the square root of 26. Both of those answers would work if you plug them into the original equation. However, because x represents the side of a triangle, we just leave the positive, or we just take the positive value, not the negative. All right, that is all. You'll practice more of these types of problems in class. Thank you so much for watching. Bye.